Greetings, Science 6 students. It's exciting to be here today because we're talking about a very exciting subject here. We're today looking at the sun. Now, apparently, in the previous book that we had, there was more time spent on the sun. And I've looked in your book for this one, and there's just not that much time in there. I'll give you a page number here in just a minute. But it's just a little portion there. They kind of mixed in with the space travel that we were looking at last week. So I'll be giving you a little more information here than your book does. But it's fabulous stuff, all about our beautiful sun. Okay, and furthermore about the seasons. I don't know if your book's going to talk about the seasons at all. Yeah, it did in the old days. Today it's maybe not. So I will add that part in. It's good information to have, so it's okay. No big deal. All right, so our sun is a blessing to us. Without it, we would not be here. We know that about stars, right? That stars have that Goldilocks zone, and we are in a Goldilocks zone right here. We get heat, light, nourishment, and our climate from our sun. Look at this beautiful picture. I think there's been a little work done on this, but just a beautiful sunset right there with the orange. This is, that's a burnt orange sky. They say that God loves the Longhorns, right? Because of the burnt orange sunset. Anyway, it's just beautiful. I don't know if those birds in there are real. Okay, so the sun, it's very difficult to study the sun, and that's because we can't really look at it. Okay, so it's something you should never look at the sun ever. It can literally damage your retina of your eye, which will make you blind. So don't do that. Okay, so we're gonna make our best guesses based on some data that has been collected about the sun, about what its structure is like. Remember, we're not even sure what's in the core of the Earth, and we live on this planet, so there's no way we know what's in the core of the sun. But we can make some guesses based on some data. On page 177, these questions are at the top of your page right there. So if you want to turn to that, we'll be answering these questions right here. They're not quite in the same order or the same format, but it will answer those questions for you. Okay, let's see. The surface of the sun, so that's the outer part here, is called the photosphere. The photosphere, okay? And that means a sphere and it means light, so that makes sense that it would be that. The sun's atmosphere is called the chromosphere. So this is the surface, and then we think of this as the atmosphere. Okay, it's floating above it, if you will. So think of the sky instead of like the blue sky with the clouds and stuff. It's a flaming, sky because coming from the prominences below. It's called the chromosphere, and then we have the outermost part is called the crown. Now that word is corona. Yes, that word's not very popular right now. I'm sure that you, unhappy with it. But it literally just means crown. To be honest, I'm not sure where the virus came up with that word. But I know how the sun came up with that word. We're going to study in a few weeks, or maybe even next week. Yeah, I think even next week. We're going to be looking at what happens when the moon comes between the earth and the sun and causes what's known as a solar eclipse. And what happens is the moon almost completely covers up the sun. It's not nearly as big, of course, but it's so much closer. And when it does that, all we can see is this outer part, and it's just like a black circle and it looks just like a crown. And that's why it's known as the corona, or the crown of the sun. There are solar, what are called faculae, which are these bright spots on the sun, okay? Those are areas of where it's hotter right there. It's sort of like a fire, how with fires moving all the time, right? So this is moving all the time, and there are hot spots that are on there, and those are called solar faculae. And solar flares come up from those. This picture, here we go, some solar flares right here. I'll show you another picture here pretty soon. It's sending it up like a giant burst of this energy being just pushed up but pulled back down by the gravity of the sun. The sun is massive. It's a star that's massive, has a massive amount of gravitational pull because of the mass of it, and it'll pull those things back in. If we try to send a probe or something to go take pictures of the sun, it gets pulled into it and burned up. Yeah, so because of the gravity being so strong. Okay, something called a solar prominence is an even larger stream of gas that pushes out into the corona there. I think I'll have a picture of that coming up. And then the solar wind is the electrical storm that radiates out from the sun. We'll talk about that in a minute too. We're seeing these, rays coming out there. Remember when you were a little kid and you drew the sun and you would have the sticks coming out from it, right? Showing the rays of the sun. Well, that is actually energy that is exiting the sun. It's very warm. You see the light coming from it. That's the manifestation of the energy that's being produced. And it's moving through space. And as it moves through space, of course, it gets to us. I think it takes about 8 minutes for the light of the sun to reach the earth. And therefore that solar wind will get to us as well. Fortunately, the magnetic poles of the earth tend to deflect a lot of that solar radiation coming, but obviously some of it comes in, which we'll get to in just a minute. And we'll see some manifestations from it. Now this picture right here is showing that we have an inner core, a radiative core, convection zone, this kind of thing. This is just a good guess based on, we're not 100% sure what is happening in the sun to cause this great furnace to burn. We do believe, I think we talked about it with stars, right, that hydrogens are fusing together to make helium. And that is called, the process called fusion or nuclear fusion, which is very difficult to do, but we believe the sun's doing that. How do we know that? We look at it through a special instrument called the spectroscope, and the spectroscope will put off a different spectrum for each type of element that is present. And we see lots of helium and lots of hydrogen when we look at it. So it's a pretty good guess. This is a picture. Now, in order for us to take a picture of the sun like this is an actual photo of the sun, we have to use very, very strong filters. So we use telescopes with very, very strong filters, and then we can get these pictures. So you can see the faculae there. We also have dark spots, and those dark spots are called sunspots. You can see here some of the prominences and solar flares coming up there. And I'm going to show you this. This is actually a video over time of the action of a particular part of the sun. It doesn't have any words, but it has some sound, mostly the machine that's moving along. Okay? Because we can't hear anything from the sun. The sound doesn't go through space. You're going to see some prominences. So you get the idea there of how those prominences happen. Notice they're all always falling back down, right, because of the gravity pulling them down that way. Here's one fixing to shoot out right there. Pretty cool stuff. I don't know if you could hear me over the sound over there, but when those prominences happen and they're headed our direction, they can mess up our cell service and stuff like that, anything that's happening in the atmosphere. So it does make a difference. I'll show you a benefit of those in just a minute. Okay, I mentioned earlier that there are also some cooler spots on the sun, and those are called sunspots. You can see them there. So this is also done with a filter. So it's actually filtering out a lot of the light, so it's kind of emphasizing those spots right there, those sunspots. Now, this, I believe, here's a sunspot, and this, I don't know if this is the actual spot just really close, or if that's an artist rendition. I'm not exactly sure. But, and when I say it's cooler, it's still, you know, too hot for anything, you know, anything to survive it, nothing like that. I want you to know how big it is, though. If we showed the Earth is about as big as that sunspot. Wow. Okay, so it's pretty large. Now, here's a guy. He is actually training this telescope on the sun. Now, never do this, y'all. Don't do it. He's got a special filter on there, okay? You cannot look at the sun ever. It will damage your eyes. And trying to look at it with one of these will just magnify it, okay? So don't do it. unless you're with an astronomer who has a filter. I have seen it. Actually, when I was at McDonald Observatory in West Texas. There was this fancy scope that was trained on there with this really great filter, and we could just watch it, sort of like that video I showed you. We watched the flares and stuff moving live. Well, 8 minutes old, but still the best we can get to. So how can you look at the sun? So one of the ways to do it is to make a box like this, okay? So notice it's a big box. It's got a piece of paper on this end. It's got a hole for your head, and it's got a little tiny pinpoint right here. It says to use aluminum foil. The reason for that is to make the pinpoint small enough. And that light will shine through there, and you can see the sun. This one looks like it's going through a eclipse right there. And so looking at that will be safe for you. Here is a fancy version you can get at a science store. They're pretty expensive. I don't even have one of these. The sun comes through here, and you can see that's the sun. And sometimes you can actually look at that and see some solar sunspots and stuff like that. I mean, so you actually can see quite a bit. And then here's the poor man's version right here, just a pinhole, and the sun coming through. See, there's supposed to be a sunspot right there, and it comes through onto your card. So you may want to try this. The pinhole needs to be really tiny, okay, and this has to do with the fact that that light travels in straight lines. Notice that dot's on the opposite side from where it came. That's because of light traveling in straight lines. You can do something fancy like this with a pair of binoculars. Okay, you can look that up online, how to do that. That's the only safe way to look at the sun. If you know somebody who is a welder with a welder's mask, they have a strong enough filter on there that you can, if there's an eclipse, you can look up there. I'd still be careful with that, however. You just never know. Just be careful. Just don't look at the sun. Now, I told you there's a benefit of all that solar wind headed our way and just streaming our way, and those solar prominences and things like this. And that is because of the magnetic poles on our Earth. They kind of pull that energy in, and it excites the ions that are in the atmosphere right there, and we end up with something known as an aurora. So, in the north, we have the aurora borealis. This is on my list of things I would like to see someday. You pretty much have to go up to Alaska if you're going to be in America, although I have a sister-in-law who lives in Michigan, and she says she has seen it. She said it wasn't super bright, but she did definitely see it in Michigan. So they do have colors. This is a photo that's probably had a filter to help capture the colors. They say that photos just can't do it. You got to see it with your own eyes. And it is kind of moving around. It's not static right here. Here you can see green is the most prominent color you see. Notice we're in a very cold place here. And it's true that the winter tends to have more activity. And furthermore, the solar flares tend to be on sort of an 11-year cycle. And those 11-year cycles tend to show more and more aurora. Down in the south, it's called the aurora australis. And that might be this picture. Yes, this is the aurora australis. I can see Australia right there. It means southern. And you can see, look, it's making that whole circle around Antarctica right there. Pretty cool stuff. We had to obviously get that picture from space. Very, very cool. Okay, so what about sunlight? We know that sunlight can damage us, right? You can get sunburn from it and this kind of thing. So there are ultraviolet rays, and we'll see where that word comes from here in just a minute. So sunlight consists of these three different types of ultraviolet rays. So we have UVA. Those are the most common. They come in, and we can have some skin damage from those. They can cause some aging and things like this to happen. If you've heard of a tanning bed, people who lay like in a bed to get a tan, they're usually using UVA rays, and it's probably not a great idea to do that. I don't know if anybody around here does. We're in Texas. We got plenty of our own sun. We don't need a tanning bed, The UVB rays, they cause the majority of the sunburn that we get. They can damage your eyes. They can damage your immune system. UVC rays are the most dangerous. These are the most energetic of them, but they never come into to the ground because God has devised a plan to keep them from getting to us. All right, so they are actually absorbed and completely changed by energetic forces called the ozone in the ozone layer out in our outer atmosphere. So the ozone is saving us from these UVC rays. I did hear something very recently about a type of UVC ray that we capture here or can make here, can somehow generate here to use for other things. So let's see though, but because UV light can also be good for us, okay? We just have to be careful with it. For instance, UVA rays help generate something known as nitric oxide in your skin. It converts it in your skin. And nitric oxide is good for reducing the risk of heart disease, relaxes your blood vessels. It's capable, but remember it's damaging, right? It actually is capable of killing bacteria. So that's good. It helps to stimulate your brain. It helps to defend against tumor cells. Remember, this is how UVA rays are good for you. I don't know about y'all, but I get a little sunshine and I just feel better. It just makes me feel better. So UVB rays right here, it actually decreases the risk of several types of cancer and of heart disease right there, digestive problems, autoimmune diseases. It improves brain function and boosts your immune system. It can decrease all causes of mortality. So it's good for you. But we already talked about how it's also bad for you, right? We just have to have a right amount. Your body needs sun exposure for optimum health. Okay, we live in Texas. We get it. In fact, sometimes down here we just get it naturally if we're walking from the car to the house. You know, people up in the northern part of our country don't have such the blessing of that. My sister-in-law who lives in Michigan and saw the aurora, yes, but she has lots of gray days and doesn't get as much sunshine. And they say that it's called the seasonal affective disorder, SAD. It kind of makes you down and sad if you don't get enough sunlight. We need sunlight to help set what's called the circadian rhythm, so we know what is day and what is night. That helps us to get a deep sleep, and more research is showing how important good sleep is for you. There are other parts of the spectrum called near infrared and red light. We'll get to that and see where that comes from. It transfers energy into your cells. They're actually making these like boxes you can sit in that have far infrared light in them, and they help to get your energy transferred into your cells. So the full blend of light wavelengths and sunlight enables our body to react in a balanced and beneficial way. But if you're there too long, damage can happen, and you can tell because you'll have sunburn. Okay, so we want to avoid sunburn, but at the same time, get some sun. It's like health food for you. We can also use UV light, and this might be what I was talking about, the UVC. I'm not exactly sure how it's generated, but one of the things is to have UV light to cleanse our toothbrushes. So here's one that you show the toothbrushes hanging in there, and the light shine. Now the light will not shine when the door is open like this is showing. The door has to be closed. You put it in there, and I think it only takes about 30 seconds for that light to literally kill the bacteria on your toothbrush. Now where is the bacteria in your toothbrush coming from? It's coming from your mouth. We have bacteria in our mouth. It's natural. They're supposed to be there. But when they stay on our toothbrush, they start to grow in our toothbrush and gross. So I'm really considering getting one of these. I found one that's just an individual one that you can just fit over your own toothbrush. You plug it into the wall and charge it, and then it gives like something like, 300 different zaps to your toothbrush, and that'll help clean it. And then you won't be putting your old bacteria that's growing back into your mouth. It could have, they're just kind of dirty. It just kind of makes things spoil a little bit. They also have one here that you can put your cell phone into. My biology students, every year, they have a project where they're going to go home and swab something, and then we bring it and put it on a plate. It's called an agar medium plate, and to see if any bacteria grow. And I had one year a student did the back of her iPod, and the growth on that was scary. I mean, it looked like there was some good pathogens growing on there. So this is a little kit. These are kind of new, where you put your phone. There's not liquid or anything there. You set it in the case. You close the lid. You have to close the lid. You push the button. The light comes on, and it zaps your phone, and it zaps all of the bacteria. Kills all the bacteria that might be on your phone. So that's a pretty cool new development there. So talking about all this infrared, that kind of business, let's talk about light. So the light from the sun, there's lots of light coming from the sun, and only a small portion of it is visible to us. We call that visible light. Okay, so if this whole thing is called the electromagnetic spectrum, all of that's coming to us from the sun, this little tiny sliver out of it right here is what we see. And if you break it into its components, we break it down into the colors of the rainbow: red, orange, yellow, green, blue, and there's indigo violet. It spells out Roy G. Biv, Roygbiv. You probably know that already. And that's all the colors of the rainbow, right? So, but on the other side of red, right? So next to red is infrared. So that's a light as well, but we can't see it with our eyes. Okay, but we can see it with special glasses, however, called infrared goggles or night vision goggles, and it actually will record heat that's coming off. So for instance, if you're in a dark forest and you're searching for someone who's lost and you put on some of those goggles, you'll see the heat from their body and you'll be able to find them. Either they're lost and you're trying to find them, or they're trying to hide from you, and you can still find them either way. Notice we have some electromagnetic spectrum over here that are larger waves, and that would be microwaves, the same waves that we use in a little oven to cook stuff, make our popcorn, right? And we have radio and TV waves over here. So the waves are already there, and people who run radio stations will find a frequency of wave and tune their radio to that frequency. And if I have something at home which will pick up that frequency, I can listen to a radio station. Same thing for the TV, although now we have cables that come to our house and our satellites that come to our house. A little different now. But the waves are still going up in the atmosphere up there. On this side, on the other side of violet, here's violet. On this side, we have ultra or beyond violet. Okay, and the waves here, so our light waves are getting faster right here, and they become more damaging. Up here we also have X-rays, and gamma rays will kill you. Okay, those are coming, from space, and our atmosphere, fortunately, gets rid of those. They don't come in and bother us. Okay, we can see this visible light all around us. Everything you're looking at right now is the visible light spectrum, but we can break it up if we want to. Using a prism, we shine the light through it, and we can make the rainbow, the whole spectrum appear right there. Yeah. Okay, I told you earlier that the sun is massive, and it has a very strong gravitational pull, so it keeps the planets in orbit around it. That's going to become important in the next couple of weeks when we start learning about the planets. So each orbit a planet makes around the sun is called a revolution, and that's the year. For the Earth to go around the sun, it takes 365.4 days. That's our year. No other planet has that same year. We'll look at each one of them and see how long each year is for them, and that's a revolution. Furthermore, the planets tend to spin on their own axis. We'll see that in just a minute. For the Earth, spinning on its own axis. That complete turning is called a rotation, and the speed at which the planet rotates on its own axis is called the day. On the Earth, our day is 24 hours long. On other planets, the days are shorter or longer depending on the planet, which we'll learn about in the next 2 weeks. So there's the sun holding the planets in their orbit. Look, we have a comet coming in. Awesome, right? And so we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, right there. Okay, we're going to learn about all those planets and various interesting details about each one of them. Oh, look, there's our asteroid belt. We know about that. So this brings about the idea of the seasons. Okay, so the sun is the driver of the seasons. And they're going to see why we have the seasons with the sun, because of the distance we are from the Earth and that kind of thing. So we have spring, summer, winter, and fall. Right now we're right here, right? We're about to enter into summer. And look at that bright sun. Look how big it is and bright. And see, it's not quite as big and not quite as big. There we go. So we're going to see why the sun is acting differently. It's fortunate that we have this. Once again, Goldilocks thing here coming in is God has devised our system so that we can be blessed with these different seasons, and we'll see why. All right, we'll see here in a minute. It has to do with the tilt of the Earth on its axis, the rotational axis right here. It's not straight up and down. It's like this, and it's spinning, and the rays of the sun are headed right at it, and notice they're going to hit the top part here more strongly because it's tilted toward it, and the bottom part not as strongly because it's tilted away from it. And let's watch a video that explains.
When I was a kid, my understanding of the seasons was that December and January were cold and covered with snow, April and May were bursting with flowers. July and August were hot and sunshiny. And September and October were a kaleidoscope of colorful leaves. It was just the way the world worked, and it was magical. If you had told me back then that 1/3 of Earth's population had never seen snow, or that July 4th was most definitely not a beach day, I would have thought you were crazy. But in reality, seasonal change with 4 distinct seasons only happens in 2 regions on the planet, and even in those 2, the seasons are reversed. But why? A lot of people have heard of an astronomer called Johannes Kepler, and how he proved that the planetary orbits are elliptical, and that the sun is not at the center of the orbit. It was a big deal when he figured this out several hundred years ago. His discovery solved a lot of mathematical problems that astronomers were having with planetary orbit measurements. While it's true that our orbit's not perfectly circular, those pictures in our science books, on TV, and in the movies give an exaggerated impression of how elongated our orbit is. In fact, Earth's orbit is very nearly a perfect circle. However, because Earth's orbit is technically an ellipse, even though it doesn't look like one, and the sun isn't quite exactly at the center, it means that our distance from the sun does change through the year. Aha! So winter happens when the Earth is further away from the sun. Well, no, not so fast. The Earth is actually closer to the sun in January than we are in July, by 5 million kilometers. January is smack dab in the middle of the coldest season of the year for those of us up north. Still not convinced? How about this? Summer and winter occur simultaneously on the surface of our planet. When it's winter in Connecticut, it's summer in New Zealand. So if it's not the distance from the sun, what else could it be? Well, we need to also know that the Earth doesn't sit straight up. It actually tilts. And that axial tilt of the Earth is one of the main reasons for the seasons. The Earth spins on an axis that's tilted 23.5 degrees from vertical. At the same time, the Earth revolves around the sun with the axis always pointing in the same direction in space. Together with the tilt, the spinning and revolving causes the number of hours of daylight in a region to change as the year goes by, with more hours in summer and fewer in winter. So, when the sun is shining on the Earth, it warms up. After the sun sets, it has time to cool down. So in the summer, any location that's about 40 degrees north of the equator, like Hartford, Connecticut, will get 15 hours of daylight each day and 9 hours of darkness. It warms up for longer than it cools. This happens day after day, so there's an overall warming effect. Remember this fact for later. In the winter, the opposite happens. There are many more hours of cooling time than warming time, and day after day, this results in a cooling effect. The interesting thing is, as you move north, the number of daylight hours in summer increases. So Juneau, Alaska would get about 19 hours of daylight on the same summer day that Tallahassee, Florida gets about 14. In fact, in the summertime at the North Pole, the sun never sets. Okay then, it's all about daylight hours. I've got it. Well, no. There's another important piece to this puzzle. If daylight hours were the only thing that determined average temperature, wouldn't the North Pole be the hottest place on Earth in northern summer? Because it receives 24 hours of daylight in the months surrounding the summer solstice. But it's the North Pole. There's still icebergs in the water and snow on the ground. So what's going on? The Earth is a sphere, and so the amount of solar energy an area receives changes based on how high the sun is in the sky, which, as you know, changes during the day between sunrise and sunset. But the maximum height also changes during the year, with the greatest solar height during the summer months and highest of all at noon on the summer solstice, which is June 21st in the northern hemisphere and December 21st in the southern hemisphere. This is because as the Earth revolves, the northern hemisphere ends up tilted away from the sun in the winter and toward the sun in summer, which puts the sun more directly overhead for longer amounts of time. Remember those increased summertime daylight hours? And solar energy per square kilometer increases as the sun gets higher in the sky. So, when the sun's at an angle, the amount of energy delivered to each square of the sunlit area is less. Therefore, even though the North Pole is getting 24 hours of daylight to warm up, the sunlight it receives is very spread out and delivers less energy than a place further south, where the sun is higher in the sky because it's more tilted toward the sun. Besides, the North Pole has a lot to make up for. It was cooling down without any sunlight at all for 6 months straight. So, as the seasons change, wherever you are, you can now appreciate not just the beauty of each new season, but the astronomical complexity that brings them to you.
Okay, so that gives us a great idea of why they happen. Now, this is kind of interesting. At certain times of the year, the way the Earth is facing the sun is where the day and the night are almost exactly equal. Okay, we call that the equinox. Okay, so there are two equinoxes every year, March and September. The sun shines directly at the equator, so that's still got a tilt. So the tilt is going like into the screen and out from the screen. Does that make sense? Or backward like that. So it's still tilted, but from its side, it's pointing right at that equator right there. So look how we have half light, half dark right there. So the length of the night and the day are nearly equal. It only happens on that one day, and furthermore, it's going to happen in March in Austin on Saturday, March 20th in 2021 at 4:37 a.m. All right, and that's when it can be exactly facing the sun. So that's the equinox, twice a year. So here we're going to see, I know these are old dates, 2014. I looked for a chart like this. I looked, and I couldn't find anything as pretty as this one. And so I had to just leave it on there. So it doesn't really matter. But you can see what happens is that it will happen in March, either the 20th. All here was the 20th. Sometimes, look here, the equinox, the 23rd or 22nd. So it just depends on like where we are in the sky in relation to the sun. Now, the solstice is a different thing. So in the solstice, we have the two of those also, the summer solstice and the winter solstice. In the summer, like for instance, right now, our days are getting longer and longer. They'll keep getting longer until about the 21st, and then they'll start getting shorter again. Then they get shorter and shorter and shorter till we get to the shortest day, which is the winter solstice. So on June 21st of 2014, it was the longest day of the year that year. So this coming June, the 20 or 21st, I don't know what it is for 2020. It'll be our longest day of the year, and then it'll start getting shorter. You probably noticed how your sun is staying out later right now, right? It's the light is staying out. We have a nice light sky later in the evening. I love it that way. Then we had the whole time change and all that business. Well, they say, I don't know if this is true, that during the equinox, since everything's even, that you're supposed to be able to balance an egg on its end like that on the equinox. Yeah, you can try it. It's not coming until the fall, right, till September. But I think that's just a myth. It's not really true. Okay, that tilt of the Earth, 23.5 degrees off of center. So here's 90 degrees. It's 23 that way. That's a pretty good tilt, actually. And then, of course, the rotation goes. The four seasons then are determined by that. The hemisphere pointing toward the sun receives direct sunlight, therefore it makes it the summer. So depending on if you're in the northern hemisphere or the southern hemisphere. I always thought it was kind of interesting that down in Australia, a lot of the students will spend their Christmas vacation on the beach. That makes sense, right? Whereas if they celebrated July 4th, it would be cold. It might be snowing. So here we're seeing it again, just a schematic here of coming along. In the summer, we're pointed right there toward the sun. And here we're pointed away from the sun. So here, the winter. And here you see it's tilted that way, but it's still going to be our equinox. So the spring equinox and called vernal. Yeah, right there. So in your book on page 183, there is a little project you might want to do. It's building a solar oven. Notice somebody's trying to cook some hot dogs right in there. This can easily be done in Texas, especially during the summer months. You take a box, it gives you an explanation how to put the foil on there and that kind of thing. And you can actually cook those hot dogs in that little oven. I don't know that you can cook many things in there. For instance, hot dogs are somewhat cooked already, and you're basically just heating them up. But it is possible to have this, and I know there are certain little solar ovens. I know I own a solar oven. It looks more like a tube, and you're supposed to be able to boil water in it. I'll need to try that this summer and see if it works. So if you want to do this project as extra credit, shoot a picture to me, and I'll get you extra credit for that. It'd be pretty cool. Okay, this is what our lab was today. Here what I'm doing is I'm showing you one of my prisms. I would have had these at class today. And then it was a sunny day, fortunately, so I held it up to the window, and look what I did. I threw a little rainbow right there onto my floor. So in our classroom at BCOC, those windows are there, but sometimes I can't guarantee the sun coming in. So we may have tried to go outside to see if we could throw them. The problem is, on a bright sunny day, sometimes you'll make a little rainbow, but it'll be so bright you can't really see it. So inside with a good window is really the best way to do it. You can use some other things for prisms if you want to try to do an at-home project. You may have a prism like this, not sure. They're pretty easy to get a hold of. I know Hobby Lobby has them. But you can use a pan of water with a little mirror set down in it, and that can cast a rainbow sometimes that way. Sometimes using, like if you go outside with a hose and spray it into the sky in a sunny day, the spray, the little drops of water will act as a prism and you'll actually see a little rainbow there. So you might want to try that as a project. Okay, and now I'm just going to talk to you about our lab today. Hey everybody, so this week you have this little kit that I gave you, right? Okay, it looks like this. There's just some plain white beads in there. What you're going to do is you're going to take the chenille stick out, right? And you're going to feed these little beads onto it, okay? One at a time. So some of you have worked with these before. You know they're magic, right? So we're just going to feed them on like this. And we're going to make a bracelet out of it. And then I'll show you what it looks like when we go outside, right? Yeah. Okay. So we're going to be exposing these to UV light with the sun. And that's going to change them, right? It's going to show different colors. And so they only show colors in response to the light. I might have enough light coming in this window to do it, in fact. So that's good. I won't have to go outside, and I can show you right away. Okay. So I think we have about a dozen that we're putting on there. I don't, you won't know what color they are until we expose them to the UV. And then at that point, if you want to, rearrange them or something like that, you're certainly welcome to do that. Okay. So essentially what I'd have you do is now take that and do, like this, and then you'd have a bracelet to wear. Yeah. Okay, and then when you go outside while wearing this bracelet, let's say if you go to the pool or something this summer, you're going to know exactly when, to put on some sunscreen or something, right? So let me take these, they're starting to actually change color a little bit, but they're mostly white, right? I'm going to take them down here to the sun. All right, let's see if we can get down here. All right, I can't tell if I'm seeing it or not. Okay, I'm going to just sit them in the sun. Wow. They're actually changing pretty quickly. Now, can you see them now? Yeah, let's put them against something light. All right, there you go. Okay, I hope you enjoy this, and you can keep it all summer. All right, see you again. Okay, so also you can do a little project with those. If you want to take your little bracelet, put it into a Ziploc bag, and then you can slather some sunscreen on the Ziploc bag, and you can see if the sunscreen really is keeping that UV light off of you. Aha, right? Because they won't turn colors in the sun if it's actually working. All right, so see if you can devise an experiment to do that. That would be fun to do. This was another thing that we were going to do today. It's called sunprint paper. Now, I couldn't send any of this home with you, and the reason is it's sensitive to light. So it's in a special packet inside here with, a dark, it's like a plastic dark thing that keeps it from being exposed to any light. And so we would have gone outside, presumably on a sunny day, and you can arrange certain things on the piece of paper. So it looks kind of blue there, you see, and you put the little leaves on there. And then you let the sun shine on it for a little bit. And then you put the whole thing in a tub of water, and that water will stop the exposure. And you'll end up with a cool picture kind of like this. All right, and it's called a sunprint. Yeah, they're very fun. Typically, I would put on there like my scissors or something from my science kit, and you could see stuff like that. So you may find some of this somewhere. Hobby Lobby has this as well. And you can try this little project at home too. Sorry, we couldn't get together for that. All right, this information was in the old book, and it's not in your book, so you're not necessarily responsible for it in the sense of a quiz or anything like that. But it's information that's useful. I'm just going to read through these really quick for you. Seasons are determined by the tilt of the Earth on its axis during its revolution around the sun. We know that. The hemisphere tilted toward the sun receives the most direct sunlight and experiences summer. When the northern hemisphere is tilted away from the sun, it experiences winter. The longest day of the year, when most of the sunlight is received for a hemisphere, is called the summer solstice. The shortest day of the year, or the period when the hemisphere receives the least amount of sunlight, is called the winter solstice in December. It takes a little less than 8.5 minutes for the sun's light to reach the earth, and during the autumnal and vernal equinoxes, the day and the night hours are about equal in length, okay, which we saw there. All right, so that brings us to the end of our presentation here about the sun, y'all, and now we're ready to learn about the solar system, okay? So the sun is in the middle, and the planets are spinning around it. So we need to have a great amount of respect for our sun and praise God for our sun. I did mention a couple times today something about sunscreen. So remember how it's healthy to get UV light on your skin, and so sunscreen is blocking that. So that would keep you from getting it. Now, why do we use sunscreen? To keep us from getting burned. So if you're going to be out in the sun a lot, then you may want to use sunscreen. My preference is to use a shirt that, like those fishing shirts that you can get at Academy, that you can lower the sleeves down, right? And you can protect yourself that way. Because there are chemicals in sunscreen, that kind of thing. But remember, a little bit of sun on you is a good thing. So, yeah, don't block it all the time. Just when you're going to be out in the sun a lot so you don't get a burn. Okay, and always do what your parents say, for sure. Okay, y'all, I will be talking to you next week when we start learning about the planets. I'm super excited about it. Okay, very good. Bye.